Hello, in this video I'd like to talk about Büchi arithmetic. So Büchi arithmetic is the first order logic of the structure, the natural numbers with addition and an extra unary operation v2, where v2 of x is going to be the largest power of 2 dividing x, and we'll say that v2 of 0 is equal to 0. So again, the first order logic of this structure is going to wind up being expressively equivalent to the regular languages. But even though we're still talking about the natural numbers like we were with the weak second order theory of one successor, we're going to be thinking about the natural numbers using a very different encoding. When we were talking about the weak second order theory of one successor, we were interested in encoding numbers in terms of which position in a word we were at. So we would encode the number n with a series of n a's. And what that allowed us to do was it allowed us to talk about sets of numbers very easily, because you could have indicator symbols at various positions throughout a word to indicate various numbers, but it left us unable to describe most operations on the natural numbers themselves. We could only really talk about successor, and I guess we could also talk about less than. But addition and multiplication were off the table, and you can prove that using the Michaux-Nerode theorem. On the other hand, Büchi arithmetic uses a different encoding for the natural numbers, specifically a binary encoding. If we encode our numbers in base 2, then we know that we can talk about addition of numbers. We've seen in a previous video that no matter what base you pick, if you're encoding numbers in a particular base 2, base 10, whatever, we can talk about addition with finite state automata. And this encoding also makes it very easy to talk about v2, right? If you have a binary representation of a particular number, you can figure out what the largest power of 2 dividing that number is very easily. You simply look at all of the zeros at the end of the number and put a 1 on to the beginning of those and ignore all of the digits before that, and there you go. You have the largest power of 2 dividing the number. And so, just as before, we have the fact that we can convert any formula in the first order logic of this structure into a corresponding automaton. So given a formula in Büchi arithmetic, so this is again a first order logical formula for this particular structure, we build it up the same way we have terms. In this case, if you have two terms, the sum of those two terms is also a term. And if you have a term, then v2 of that term is also a term. And you just build up in exactly the same way that we've done before, the first order logic of this particular structure here. So if we have a formula in that first order logic, we can construct a corresponding automaton such that a sub phi accepts the tuple binary encoding of some numbers n1 through nk, if and only if phi is actually true of n1 through nk. So for instance, if we had a formula that looked like v2 of x plus y is equal to z, then we can construct a corresponding automaton, a sub phi, for this formula here. And the fact that phi holds of 10, 30, and 8, right? If we take v2 of 10 plus 30, the largest power of 2 dividing 10 plus 30, the largest power of 2 dividing 40 is going to be 8. And so this formula is true of 10, 30, and 8. This is going to correspond to the fact that the automaton accepts. We encode each of these numbers in binary. So 10 is 1010, 30 is 11110, and 8 is 1000. Now, normally, if we were talking about words, we'd want to pad on the right, right? We would want to add in a padding character on the right of these things. But here's the thing, we're talking about binary numbers, right? We want to pad binary numbers with zeros on the left. If we padded them with zeros on the right, they'd wind up turning into different numbers, right? If we took this number and padded it with a 0 on the right, it would turn into 20 as opposed to 10. So we need to pad on the left. And this gives us an input. Each column here represents a single character that we're going to input into our automaton, a sub phi, and our automaton a sub phi is going to accept this particular 5-character input. And don't forget that the natural way of reading in binary numbers is from right to left, right? You want to, generally speaking, you want to start with the least significant digit and then work your way up to the most significant digit. On the other hand, remember that the regular languages are closed under reversal. So whether or not we build one automaton to read this word from right to left, or another automaton, which is the reversal of the original automaton, to read the word from left to right, it doesn't matter. But it does matter which way we pad our numbers. It's really important to pad your numbers on the most significant digits, not the way that you would normally pad words. And the proof of this fact is almost exactly identical to the way that it's been in the past few videos. If we have a particular formula, our first step is going to be to relationalize the formula. Instead of having a formula that has addition and v2 going on at the same time, or multiple instances of addition or multiple instances of v2, we're going to want to break these formulas apart so that each atomic formula only refers to one operation, and that's it. For instance, if we wanted to break this formula apart, we would have to say that there exists a w such that w is equal to x plus y, and v2 of w is equal to z. This allows our base case of our proof by induction to only have to worry about these sorts of very basic atomic formulas, as opposed to atomic formulas that contain a whole bunch of addition and v2 applied together recursively. There's going to be an infinite number of formulas. We'd have to do some sort of induction on that. It's just gross, and we don't want to deal with that. This way, our base case formulas are pretty much only going to look like this. Some variable is equal to the sum of some other variables. v2 of some variable is equal to some other variable, or maybe one variable is equal to another variable. And that's all that you have for atomic formulas. So those are the base cases. Again, you want to prove this fact for all of those base cases, so you need to turn all of these things into finite state automata. We've talked about how to turn addition into a finite state automaton when we're representing things in base 2, and I'll let you figure out how to turn v2 into a corresponding finite state automaton. The proof then continues by induction on the construction of the formula from the atomic formulas, making use of the closure properties of the regular languages. One of the really exciting consequences of this fact here is that if we got rid of v2, this would still be true. If we have a formula in the first order logic of the natural numbers with just addition, it's going to be a formula in the first order logic of Büchi arithmetic, just one that doesn't involve v2. So we can construct a corresponding automaton for that formula, and this allows us to study the first order logic of the natural numbers with addition. For instance, if we had a sentence, a formula with no free variables, and we wanted to determine if it was true or not, we would use this construction here to construct a corresponding automaton. That automaton wouldn't have any inputs. We don't input anything into that automaton. We just ask if the automaton that we construct it accepts or not when we don't feed any input into it. And that tells us if the corresponding sentence that we turned into that automaton was true or false. The natural numbers with just addition is called Presburger arithmetic, and it's extremely well studied and well understood, and it has some very nice properties. One of the most important properties of Presburger arithmetic is that it is not powerful enough to be subject to Gödel's incompleteness theorem. Gödel's incompleteness theorem applies if we're studying the first order logic of the natural numbers with addition and multiplication. But if we get rid of multiplication, if we just have the natural numbers with addition, then the theory can actually be axiomatized in such a way that everything can be proved from the axioms. You can, as we've seen, determine whether any formula is true or false. It's a very nice structure. It's not quite as nice as possible. You need infinitely many axioms for this structure, but they're relatively nice axioms. Specifically, it's this induction axiom that winds up giving us infinitely many axioms. What we want to do is we want to say that induction works for every formula. But unfortunately, we can't say for every formula, right? This is the first order logic of the natural numbers with addition. Our variables and quantifiers are only allowed to refer to natural numbers, not formulas. And so in order to get this induction axiom to actually work, we need a separate axiom for each possible formula that you could want to apply induction for. And this actually gets a little bit weird because, for instance, you're just going to want to iterate through all possible formulas when you're expressing these induction axioms, and as part of that, you're going to iterate through a whole bunch of formulas that, for instance, aren't true of 0 or don't satisfy this induction step. And so the induction axiom doesn't actually say anything useful about them. But that's okay, we'll toss them in there anyway. It's easiest to just have, this is called an axiom schema. It's easiest just to have an axiom schema that iterates through all formulas as opposed to just individually picking out the ones where it's actually interesting that induction works for. Another nice thing about Presburger arithmetic is that we know exactly what we can say in this first order logic. And it's pretty much just modular arithmetic. We can say that a particular number has a certain remainder, mod 2, or mod 3, or mod 4, or so on and so forth. And that's pretty much all that we can say in this particular logic. It's also worth noting that we can talk about less than or equal to in Presburger arithmetic. This is very straightforward. You just say that x is less than or equal to y if there's some z that we could add to x in order to get y. So let's focus on what we've done so far. We've worked out a way to take formulas in the first order logic of Büchi arithmetic and turn them into corresponding finite state automata. This tells us that the first order logic of Büchi arithmetic is at most as expressive as the regular languages. But we want to show that it's expressively equivalent. We want to show that we can take any regular language and describe it by a formula in Büchi arithmetic, and we can do that. So for any formula phi of the weak second order theory of one successor, and we can replace this. This could be for any regular language, L, or it could be for any automaton, A, but the proof is actually easiest if you think about this in terms of formulas of weak S1S or some other first order logic structure. There's a corresponding formula, rho, of Büchi arithmetic such that phi holds of some first order variables and some second order variables if and only if rho holds of an encoding of those first and second order variables. We're going to want to translate these variables appropriately because this fact does not work unless we actually do some translation. So here we translate first order variables to 2 to the power of that first order variable. And that makes sense, right? If we're thinking about representations of these first order variables in terms of words, it's going to be, you know, maybe n a's followed by a b or something like that. Whereas here, the binary representation is going to look roughly the same. It's going to be a 1 followed by x1 zeros. And then when we have finite sets of natural numbers, we can translate those again via our encoding to binary numbers And it's really nice how to express this. It's just the sum over all natural numbers in the set of 2 to the power of that natural number, right? That's essentially taking all of those positions and making them 1 in the base 2 representation of that number. And it's worth noting, this isn't a particularly lossy encoding. Sure, these numbers all wind up always having to be powers of 2, and so we can't work our way backwards if we're working with something that isn't a power of 2. But here, this could be any number, right? And we can view that number as a binary encoding of a finite set. We can always translate back when we're talking about the second order elements of this structure. Now, if we were trying to prove this for every regular language or every finite state automaton, we could just describe what it means to be a finite state automaton in the language of Büchi Arithmetic. And the proof would look very similar to how it did in the previous videos. However, if we're proving it this way, we want to prove by induction on the construction of the formula phi. Again, relationalizing everything just to make our lives a little bit easier. So for instance, when we're trying to prove this for the base case of phi of xy, so phi is a formula of weak S1s, so let's say that that formula is that x is equal to the successor of y. This is one of our basic atomic formulas that we could expect showing up when we relationalized our structure. We want to translate this to a formula of Büchi arithmetic that holds when we're encoding x and y as 2 to the x and 2 to the y. So that's going to mean that n is going to be our encoding of x, and we're going to require that n be a power of 2. And we can do that simply by saying that n is the largest power of 2 dividing n. And we're going to require the same thing of m. And so what does it mean? If n is going to be 2 to the x, and m is going to be 2 to the y, and x is going to be 1 plus y, then how are n and m related? Well, it's simply going to be the case that x is 2 times y. In particular, x is going to be equal to y plus y. It's worth taking a moment to note that Büchi arithmetic can talk about multiplying by specific natural numbers. It can talk about multiplying by 2, it can talk about multiplying by 3, so we have y plus y, that's perfectly fine. Multiplying by 4, whatever. The thing that Büchi arithmetic can't talk about is when we want to multiply two variables together, and that's really where you get into trouble with Gödel's incompleteness theorem. So let's take a look at another base case. Suppose that we want to translate the formula in weak S1s that x is an element of the set y into Büchi arithmetic via this translation. Well, what we're going to want to translate this into is a formula that somehow expresses that n is a power of 2 that shows up as a 1 when we're representing m in base 2. So for instance, if we had the number 10, we would represent this in base 2 as 1, 0, 1, 0. In other words, 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. And of course, we could get rid of these coefficients and just express this as 2 to the power of 3 plus 2 to the power of 1. And so what we're asking is n one of these powers of 2 that show up when we take our original number and decompose it in this fashion? So in particular, we would want it to be the case for 10 that rho of 8, 10, because 8 shows up in the power of 2 decomposition. And we'd also want it to be the case that rho of 2, 10, because 2 shows up in the binary decomposition of 10. But we wouldn't want it to be the case that rho was true of anything else, comma 10. So we're trying to find a formula in Büchi arithmetic that expresses this particular relationship. And I encourage you to pause and try to figure out what that formula is. So written out in the language of Büchi Arithmetic, this formula is so we first want to express that n is in fact a power of 2. That's important. Weird things would happen if n wasn't a power of 2 and we were trying to do this sort of construction. And there's going to be numbers p and q such that m is p plus n plus q. We're going to want p to represent the contribution of the binary digits in lower places than n. We're going to then say that n is part of the contribution of these binary digits in constructing m, and then we're going to want q to be the contribution of all of the terms in higher places than n. So suppose that we had a binary number like 10110110, and we wanted to express that this digit here was part of the binary representation of that number. Then we want to break this number up into 3 parts. We're going to have p, we're going to have n, and we're going to have q. N is just going to be this digit here, so 10000. P is going to be all of the digits in lower places, so p in binary is going to be 110. And q is going to represent all of the digits in higher places. In other words, 1010000. And then when we add these 3 pieces together, it's going to give us our original number. So what are the constraints on these contributions here? Well, the constraint on p is easy. We just need p to be strictly less than n. Q, on the other hand, could be 0. It could be the fact that we're looking at the highest place and there's no contribution from higher digits of the number. So Q could be equal to 0, or we want Q to have a whole bunch of zeros here. In particular, it needs to be the case that the largest power of 2 dividing Q is strictly greater than n. In other words, it's just a whole bunch of zeros over here. This here is the largest power of 2 dividing q, and it's going to be at least twice n. And don't forget that we can talk about less than or equal to just by taking advantage of the fact that we're talking about addition of natural numbers. And this pretty much covers the base case of the construction of the formula phi when we do our relationalization. And then you just prove by induction. And the proof by induction is really easy because in order to translate a formula of the form f and g, all you need to do is translate f, translate g, and put an and between them. Because this Büchi arithmetic is also a first order logic. So the proof by induction on formulas is really quite straightforward in this case. But if you're not happy with that, again, you can do the sort of proof that we've seen previously, where we construct a finite state automaton out of some formula in Büchi arithmetic. There's a bit of an interesting historical oddity here. In Büchi's original paper, where he talked about the weak second-order theory of one successor, he also talked about this structure here, except instead of talking about this structure having a v2 operation in it, he just had a predicate, which he called pw2, that simply told you true or false, are we looking at a power of 2? And he tried to do exactly the same construction to convert from the first order logic of this structure to the weak second order theory of one successor, which he had proved a lot of things about already in the paper. Unfortunately, when he got to this step here, he made a mistake, right? You can write this bit of the formula here. This bit was just saying that n was a power of 2, and so we could just replace it by directly saying that n is a power of 2. But this bit of the formula here, he wrote as q is greater than or equal to n plus n. And that doesn't actually work. That doesn't ensure that q is the set of digits to the right of n in the binary representation of the number. it could be the case that there's also some stuff going over in these less significant bits as well. And so if you actually check his work, if you actually check the formula that he claims expresses this predicate here, it does not. This error was pointed out in a review of Buchi's paper by MacNaughton in the Journal of Symbolic Logic. And I think I've tracked down the story of how this correction was made, forming what we call Büchi Arithmetic nowadays, which actually is expressively equivalent to the regular languages. But I'll leave that story down in the video description in case I learn more or have to change it. One can, of course, ask, well, what happens if we're interested in studying this structure where we have the natural numbers with addition and just a predicate to recognize powers of 2? Not V2, but the original logic that Büchi was studying. Is it the case that we can still somehow make this proof work? That the proof itself was wrong, but that the result was correct? Or is it the case that the result was incorrect? And it's actually the case that it was incorrect. If you replace V2 by a predicate that recognizes powers of 2, this actually reduces the expressive power of the language. Remember that we can decide if something is a power of 2 using V2, but we can't go backwards. We can't, just by using the ability to recognize powers of 2, figure out what the largest power of 2 dividing a number is, regardless of how complicated a formula we use to do that, when the only other thing that we have to talk about is addition. And this actually leads us into a very exciting field of study, where we're interested in what structures are equally expressive to what other structures, and what structures are less expressive or more expressive than which other structures, and we can get this whole hierarchy of structures in terms of their expressive strength. And I hope to talk a little bit about that a few videos down the line. So thanks for watching. Let me know if you have any questions or have trouble performing any of the constructions in this video in the comments, and I hope to see you in a future video.